Hello everyone, I'm Akash. Today's video is going to be very interesting. We will solve this linear algebra question that I have posted on our YouTube channel community post on July 14th. Question is, we have given 3 by 3 matrix A with column vectors 0, 0, minus 1, 0, minus 1, 0 and minus 1, 0, 0. Then we have to determine which of these given statements are true. We can solve this question in two ways. First, by using standard procedure, in which we have to find the matrix P which diagonalizes the matrix A. But this method is time consuming. Another way by which we can solve this question is by using results and theorems. If we use some results and theorems to solve this question, then we can solve this question in just 2 minutes. So, if this type of question is asked in exams like CSIR NET, GATE, where the time is very crucial, then we must solve this question by using results and theorems. However, there are exams like IIT JAM, NBHM, CMI, where the subjective type of question is also asked. So, if this type of question is asked as subjective type of question, then they will ask you to find the matrix P which diagonalizes the matrix A. In this case, the results and theorem don't work. You cannot find the matrix P which diagonalizes this matrix A by using some results and theorem. In this case, you must go through the standard procedure. So in this video, we will solve this question by using both the methods. First by using standard procedure and then by using results and theorems. Please don't skip the standard procedure because this will help you in understanding underlying results more deeply. So let's begin the solution. The statement in A is diagonalizable over R. So what is diagonalizable matrix? A square matrix A is said to be diagonalizable if A is similar to some diagonal matrix. Okay, a square matrix A is said to be diagonalizable if it is similar to some diagonal matrix. That is, if there exists an invertible matrix P such that P inverse AP is equals to the diagonal matrix. So a square matrix A is diagonalizable if there exists an invertible matrix P such that P inverse AP is some diagonal matrix. This is by definition of similar matrices. So according to our standard procedure, we have to first find out the matrix P which diagonalizes A. And by that procedure, we know that the column vectors of P are eigenvectors of matrix A. So we have to find first of all eigenvectors of a matrix A. So we will first find out eigenvalues of A and then we will find corresponding eigenvectors. So to find the eigenvalues of a matrix A, let's consider the determinant of lambda I minus A. This determinant is equals to the lambda 0 plus 1 0 lambda plus 1 0 plus 1 0 and lambda. So let's evaluate this determinant. Lambda times lambda plus 1 minus 0 plus 1 times 0 minus lambda minus 1. Okay, so this is nothing but equals to lambda square times lambda plus 1 minus lambda minus 1. This can be written as lambda square times lambda plus 1 minus in bracket lambda plus 1, which is nothing but lambda square minus 1 times lambda plus 1, which can be written as lambda minus 1 times lambda plus 1 times lambda plus 1. Okay, so this is the characteristic polynomial of A. Okay, let's denote this by the characteristic polynomial of the matrix A. Okay, and its roots are eigenvalues of a matrix A. And clearly we can see that here lambda equals to 1 is a root and lambda equals to minus 1 is also a root. So we see that lambda equals to 1 is an eigenvalue of matrix A with algebraic multiplicity 1, and lambda equals to minus 1 is an eigenvalue of a matrix A with algebraic multiplicity 2. Okay, so up to now we have seen that lambda equals to 1 is an eigenvalue with algebraic multiplicity 1, and lambda equals to minus 1 is an eigenvalue of a matrix A with algebraic multiplicity 2, and this is the characteristic polynomial of matrix A. Now let's find out the eigenvectors corresponding to these eigenvalues. For this, we consider the homogeneous linear system A minus lambda I of x equals to 0. Because by definition of eigenvector, we know that x is an eigenvector corresponding to eigenvalue lambda of A if and only if it is a non-zero solution of this homogeneous linear system. So we will solve this homogeneous linear system for different values of lambda and find out the different eigenvectors. Okay, so let's consider this homogeneous linear system for lambda equals to 1. Okay, when lambda equals to 1, this will become A minus I. Okay, when lambda equals to 1, this matrix will become A minus I. So when lambda equals to 1, the matrix A minus I is minus 1, 0, minus 1, 0, minus 1, minus 1, that is minus 2, 0, minus 1, 0, and minus 1. Okay, this is the matrix A minus I, and let's write this vector as x1, x2, and x3. So this is the homogeneous linear system that we have to solve. Just we will reduce this coefficient matrix to echelon form by using standard elementary row operations. Okay, so I will multiply the first row by minus 1, and after that I will add the first row to the third row. So we will get 1, 0, 1, 0, minus 2, 0, 0, 0, 0. Okay, and this column vectors remain same because all entries are 0. And in the next step, I will divide the second row by minus 2. So this will reduce to the 1, 0, 1, 0, 1, 0, 0, 0, 0. Okay, and let's write this x1, x2, x3, and 0, 0, 0. This column remains same because all entries of these columns are 0. Now let's write the corresponding equations. This is an echelon form. Okay, so let's write corresponding equation. X1 0 times x2 plus x3 equals to 0 and x2 equals to 0. Okay, as the first row has leading entry and second row also has leading entry, so the leading variables are x1 and x2, and what will be the free variable? X3. So assigning free variable arbitrary value, say x3 equals to r, where r is any arbitrary real number, then we get x1 equals to minus x3 and x3 is r, so x1 equals to minus r, x2 equals to 0, and x3 equals to r. So writing this in a column form, we get x1, x2, x3 equals to r times minus 1, 0, 1. Okay. So if we choose, we can take any value of r, and for different values of r, we get different eigenvectors. So there are infinitely many eigenvectors corresponding to this eigenvalue lambda equals to 1. So for simplicity, we will choose r equals to 1. So the eigenvector is minus 1, 0, 1, corresponding to eigenvalue lambda equals to 1 of A. So remember this. This is an eigenvector of a matrix A corresponding to eigenvalue lambda equals to 1. So up to now, we have seen that this vector minus 1, 0, 1 is an eigenvector of A corresponding to eigenvalue lambda equals to 1. Now let's find out the eigenvector of A corresponding to eigenvalue lambda equals to minus 1. So we put lambda equals to minus 1 in this homogeneous linear system. So it will become A plus I. So we have to construct the matrix A plus I. So A plus I will have entry 1, 0, minus 1, 0, minus 1 plus 1. It will become 0, 0, minus 1, 0, 1. Okay. So this is the matrix A plus I. And this column vector x1, x2, x3, and this is 0, 0, 0. We have to solve this homogeneous linear system. Okay. So again, we will reduce this coefficient matrix to echelon form by using standard elementary row operations. So let's add the first row to the third row. Okay. So this system will become 1, 0, minus 1, 0, 0, 0, 0, 0, 0. Okay. And this 0 vector remains same because all entries are 0. Okay. And clearly this matrix is in echelon form, so we can write the corresponding equation x1 0 times x2 minus x3. So x1 minus x3 equals to 0. So from here we see that x1 is in leading variable and x2 and x3 are free variable. Okay, x1 is in leading variable and x2 and x3 are free variable. So assigning free variable arbitrary values, say x2 equals to r and x3 equals to s. Then from here, this implies x1 equals to x3 and x3 equals to s. So x1 equals to s. x2 equals to r and x3 equals to s. Writing this in a column form, we get the column vector x1, x2, x3 is equals to s times 1, 0, 1 plus r times 0, 1, 0. Okay. So for different values of s and r, we get different eigenvectors corresponding to eigenvalue lambda equals to minus 1. We have substituted here lambda equals to minus 1. Okay. So for different values of s and r, we get different eigenvectors corresponding to eigenvalue lambda equals to minus 1. For simplicity, we will choose s equals to 1 and r equals to 1. So we get the eigenvectors 1, 0, 1 and 0, 1, 0 corresponding to eigenvalue lambda equals to minus 1. So remember this. Up to now, we have seen that these three are eigenvectors of a matrix A corresponding to their respective eigenvalues. What you can see from these three eigenvectors? Clearly, they are linearly independent eigenvectors over R. To see that, simply consider the matrix with these three eigenvectors as their column vector and compute the determinant of that matrix. You will see that that determinant is non-zero. So these three vectors are linearly independent vectors over R. Okay, and there is a result that if n by n matrix A has n linearly independent eigenvectors, then A is diagonalizable over R. So clearly here A is a 3 by 3 matrix and A has 3 linearly independent eigenvectors over R. So A is diagonalizable over R. So the statement in A is a true statement. So we mark it as correct. Now, as these three vectors belongs to R3 and they are linearly independent, so they form basis for R3. They form basis for R3. Now, is these three vectors satisfy this condition? What this condition is about? This condition says that is these three vectors are orthogonal to each other? Let's verify. Simply compute their inner product. Let's denote this vector by u1, this by u2 and this by u3. Now let's compute the inner product of u1 and u2. Standard inner product on R3, okay? And the standard inner product on R3 is nothing but the dot product, okay? So we compute the dot product of these two vectors. So minus 1 times 1, which is nothing but minus 1, plus 0 times 0, plus 1 times 1, which is nothing but 0. So by definition of orthogonal vectors, we see that as inner product of u1 and u2 is equals to 0, so u1 and u2 are orthogonal to each other. Similarly, you can show that for any two vectors in these three vectors, the same condition holds. That is, inner product of ui comma uj is equals to 0 for every I comma j belongs to 1, 2 and 3. Okay. So there exists a basis of R3 consisting of eigenvectors of A which satisfy this condition. Okay. So the statement in B is also a true statement. So we mark it as correct. However, up to now, we have not found the matrix P which diagonalizes the matrix A. As I have told earlier that according to the standard procedure, the column vectors of P are eigenvectors of matrix A. Okay. So simply write the matrix P as matrix with these three column vectors. You can take any order of your choice. So I am taking this as a first column vector, this as a second column vector, and this as a third column vector. Then you can see that you can easily verify that this matrix P diagonalizes the matrix A. To verify that, you have to compute the product P inverse AP, and you have to verify that this product is equals to some diagonal matrix or not. If this product equals to some diagonal matrix, then this matrix P diagonalizes A, and you can simply verify that in this case P inverse AP is equals to the matrix 1 0 0 0 minus 1 0 0 0 minus 1, which is diagonal matrix. So this matrix P diagonalizes the matrix A. So this is the required matrix P. Now let's move to the statement in C. The statement in C is the characteristic and minimal polynomial of A are same. Is this a true statement? No. We can easily verify that this is a false statement. Let's first recall what is minimal polynomial of a matrix. Minimal polynomial of a matrix is a monic polynomial of a lowest degree which annihilates that matrix. So if I denote m lambda of A is a minimal polynomial of a matrix A, then it is a monic polynomial of lowest degree which annihilates A, which annihilates A means that is m lambda of A is equals to 0 matrix. This is not a 0 real number, it is a 0 matrix. Now, the given matrix A is a special type of matrix and it is called anti-diagonal matrix. Okay. And for this anti-diagonal matrix, you can verify that it satisfies A square is equals to identity matrix. Okay. A square is equals to identity matrix. So from here, we have A square minus I is equals to 0 matrix. So we see that the matrix A satisfies lambda square minus 1 equals to 0, this equation. Okay. So the matrix A satisfies this equation. That means it is an annihilating polynomial. Lambda square minus 1 is an annihilating polynomial for a matrix A. Okay. But by definition of monic polynomial, it is a least degree, it is a monic polynomial and it is of lowest degree which annihilates the matrix A. Now, if I factor this as lambda minus 1 times lambda plus 1, okay, so is this matrix satisfy this polynomial or this polynomial? You can clearly verify that A minus I is not equals to 0 and A plus I is also not equals to 0. Okay, these two factors, okay, that is these two factors are not annihilating polynomial for the given matrix A. So the only choice is this. So it is a lowest degree polynomial which annihilates the matrix A. And clearly you can see that it is a monic polynomial. Coefficient is 1. So it is the lowest degree polynomial which is monic and which annihilates the given matrix A. So the minimal polynomial for the matrix A is m lambda of A is equals to lambda square minus 1. Okay. And clearly it can be written as lambda minus 1 times lambda plus 1. Okay. So this is a minimal polynomial for a matrix A and you can clearly see that it is not equals to the characteristic polynomial for a matrix A. So the minimal polynomial of a matrix A is not equals to the characteristic polynomial of a matrix A. Okay. So the statement in C is incorrect, so we mark it as incorrect. Now let's move to the statement in D. The statement in D is there exists a 3 by 3 matrix B such that AB equals to C where C is orthogonally diagonalizable over R. Is this a true statement? Yes, this is a true statement. This is just a rephrasing of word. Note that determinant of A is non-zero. Okay, determinant of A is non-zero. So this implies A is invertible matrix. So this implies there exists a matrix B such that AB equals to identity matrix, where B is nothing but A inverse. Okay. So there exists a matrix B such that AB equals to identity matrix. So AB equals to C, where here C is identity matrix. And we know that identity matrix is orthogonally diagonalizable over R. So the statement in D is a true statement. Okay. Now, can we solve this question by using results and theorems in just 2 minutes? Yes, we can solve this question in just 2 minutes. Let's solve it. Clearly, A is symmetric matrix. You can verify that A transpose equals to A. And for the symmetric matrices, we have the result symmetric matrices are orthogonally diagonalizable. So as A is symmetric matrix over R, so A is orthogonally diagonalizable over R. As A is orthogonally diagonalizable over R, so A is diagonalizable over R. So the statement in A is true statement. Moreover, as A is orthogonally diagonalizable over R, so there exists an orthogonal matrix P such that P inverse AP is equals to diagonal matrix D. And as P is orthogonal matrix, so the column vectors of P are orthogonal vectors. Okay, so the column vectors of P satisfies this condition. But we know by theory that column vectors of P are eigenvectors and they are linearly independent because A is diagonalizable. So there exists a basis of R3 consisting of eigenvectors of A which satisfy this condition. Okay, so statement in B is also a true statement. Okay, so by same result, statement in B is also a true statement. And for C, you can simply note that for each matrices of this type, that is, okay, for matrices of this type, the minimal polynomial is always equals to lambda square minus 1. Okay, the minimal polynomial is always equals to lambda square minus 1. So the statement in C will be incorrect because we have seen that the characteristic polynomial is something different, not this. Okay, and clearly D is obviously a true statement as we have seen here. So we can solve this question in just 2 minutes by using this result. So if you found this video interesting and helpful, then please like and share this video and subscribe to our YouTube channel. Thank you for watching.